Now we've gone through the process to ensure that our desired pole of -2 plus or minus 2j, or the desired dominant pole of our closed loop system, is going to appear on the root locus by selecting that the 0 for our PD controller is 4. So now we're ready to actually make our root locus and determine what the gain k should be so that we get exactly the desired pole with our controller. So what we can do is make our root locus of this g prime, s plus 4, now that we know it's 4, s plus 4 over s squared plus 2s. That's what we're going to put into our root locus, and we're going to see what gain it takes to get to our desired poles. So jumping into MATLAB, I'm going to make I'll call it GRL in MATLAB, and this is going to be that G prime or GRL that was just on the slide. So notice here, again, I'm putting in the 4, now that I've determined that the Z had to be 4 in order to make sure that our desired pole is on the root locus. So this is the transfer function I'm going to put into root locus. And we make the root locus for now this G prime. All right, so we see right away the shape has certainly changed and how it has that curve that we're looking for. And we can find now what gain it's going to take in order to make sure that we have the desired dominant poles. So I'll click on here, and we want to go to our desired pole. So we can get pretty close to it. All right, so right there, we see that the pole on our root locus, -2 plus or minus 2j. Remember, I really only have to click one since they're automatically going to come in complex conjugate pairs. I will show both here just for the sake of it. But if we select one, we've automatically selected the other one. All right, so either one, we see that it tells us to use a gain of 2. So if our k value is 2, then the poles of our closed loop system will be at -2 plus or minus 2j. So I'll recreate here on the slide, and now we can put it together. So the closed loop system is always going to be, for any controller, kg prime over 1 plus kg prime. This is, of course, if we're ignoring the actuator and the sensor that we've been doing here. But that's going to be for our negative feedback loop, what we get. So g prime we determined in the previous step where we selected that the 0 we add from the derivative controller should be 4 times our plant. So that I'm replacing with the s plus 4 over s squared plus 2s. And now from the root locus step, I know that the k value should be 2. So I can plug all of this in, and I'm going to get here that do this multiplication. So I use Mathematica to expand this out just so I can investigate how this is going to work. So looking at the closed loop system I get and putting it into the nice form we were using before, we see that the denominator is indeed s plus 2 plus or minus 2j, meaning that the poles of the closed loop system, the dominant and actually only poles of the closed loop system, are indeed -2 plus or minus 2j. That's exactly what we wanted to happen, and we see that it does mathematically here. And if we look at the numerator, we do have a 0 in the numerator. So it's a second order system, but it does have this extra 0. And I factored it out the way we were doing before when we were looking at extra poles, extra zeros. So we do have an extra 0 at -4. So one thing we have to keep in mind with the root locus method is that when we're going through all the design process, when we're selecting our poles, we are treating the system as though the dominant poles entirely determine how the system is going to behave. It is not accounting for extra 0, a third pole, a fourth pole even, 1 or 2 zeros that we're adding into the system. And we know that those modified systems are not going to act exactly like the second order baseline system that we usually are looking at. Here we see that we have this 0 at -4, so that will impact the behavior of this system. The real part of the dominant pole is -2. We have a 0 at -4 that's within 4 times the real part of the pole, so we should expect this to have an influence on our system. And we know that that extra left-hand plane in general is going to increase the overshoot and decrease the peak time from the second order system baseline. Now we didn't know beforehand what the gain should be in the system to get our desired closed loop pole location. It turned out to be 2, as we saw from the root locus, but it could turn out that the gain can be very, very high. And we know from investigating before that high gains are potentially going to increase that input effort or that input function a lot. And that's something we often want to avoid here. We're going to see when we go into simulating this, though, that I can't just put in Simulink what the 0 of 4 we found and what the gain of 2 is that we found. We're actually going to implement it using 2 gains as illustrated here. So originally in the design stage of the controller, it was this k times s plus z, or 4, and we found it was 2. We're actually going to find that we want to implement 2 gains here, a kd and a kp, and that's where these are coming from. So I want to expand this out, so I have a ks plus 4k, and what we're going to see is that the term with the s is kd, that's going to be the 2 that we found, and then kp is actually going to be our 0 times the gain of 8. And that's how I'm going to be implementing this in the controller step when we validate it using Simulink. So again, for the PD controller, we actually have a gain for the proportional part, the kp, in this example right now 8, and a gain for the derivative part, that is going to be kd, and that's going to be 2. All right, so going into MATLAB, I'll open up the Simulink file here. So we see it looks a little bit different than the proportional controller that we were dealing with before, and it looks different than the integral controller we were dealing with. When we implement this, and the way that, depending on how in hardware we do it, it might be a kind of a similar step, is that I'm going to take my input, if we track it along here, and this is that junction where it compares it to find the error. We have the output from the open loop or the plant coming up here, and the error is coming out. In implementation in Simulink, I'm actually going to split that error out. So the error is going to feed into the proportional part. Right now I haven't defined kp, so that's why it's in red, but that is the proportional branch, and that's just like what we saw with the P controller alone. So the error goes through that, it gets amplified, and then it's going to come out the other side, and we'll hold off on it for now. And then the error is also going to branch into this derivative branch. So it's going to go through the kd amplification that we just found, and then it's going to go through the s, which is going to take the derivative. Again, from in the Laplace domain, multiplying by s is a derivative, dividing by s is an integral. Now when we're implementing this in Simulink, we can't just, unfortunately, put an s here. So if you see what I did here, it doesn't like if I say that the numerator is like 1, 0. Let me open this up. I can't just have it be 1, 0 over 1. It doesn't like it when the numerator is of a higher degree than the denominator. So to effectively make it s, I'm making the s term in the numerator really small, this 1 times 10 to the negative 3. I could make it smaller, but it's effectively a coefficient of 0. So the s in the denominator basically isn't doing anything, and then the constant term. There's other ways in Simulink that we can go through this. There is a toolbox for this, but it's a little bit more advanced than what I want to get into now. Effectively, this transfer function is s over 1, but I have to give the s in the denominator a very small value to make it work. Right, so that's why I'm calling it s in quotes. So the error goes through the proportional part with its gain, it goes through the derivative part with its gain, and then I'm going to add them back together because that is the total input that should be going into my system. Now another little feature that I put into here was, I'm calling it a limiter, but it's a block called a saturation block in Simulink. And if I open up that, what this is going to do, it limits what the value of EI actually can be. A big drawback of using a derivative, a derivative controller in a PD, or as we'll see a PID, or anything that involves a derivative, since we're seeing the rate of change of error initially where our error is 0 because we're at rest, and then we have an extremely high error because the reference signal, the output is 0 and the reference, like in this, is 5. The slope, or the rate change of the error, is extremely high. It's basically infinite initially, which means that the derivative part is going to be extremely high and approach infinity. It has this big, what's called a kick in our controller. Now, this is good because it really gets the controller started in correcting the error and bringing it to 0, which is to say bringing the reference and the output equal. But it might be very high and not really even achievable depending on what the actuator into the system is, or like in this, let's say it's an electronic system, it might require an extremely or even infinitely high initial voltage as the input. Well, practically speaking, we can't do that. We can't provide it this infinite input. So what I do here, I'm selecting right now just arbitrarily that the most EI could be is 25 or negative 25. So even if coming out of the controller, it's saying we need 1,000 volts or an infinite number of volts, it's going to say, you know what, the most we can apply is 25. And it's going to limit the practicality of our controller. I'm putting this in here just so we don't get some ridiculous infinite input demand into our system. Even though the controller wants it that way, we can't supply it. Now, just putting 25 and negative 25 here arbitrarily, in a real system, you could put in practically what is the most voltage, the most force, the most whatever the input is that your system, that your input system can actually handle. This step is optional, but makes it a little bit more real world. But this is going to happen, this issue is going to happen anytime we're using a derivative in our controller. All right, so coming out of the limiter or the saturation, that's going to cap it at 25 or negative 25 before it goes into the plant. And then the output of that is going to come back and feed into this negative feedback control. All right, so it's a modification certainly of what we saw from the previous controllers. We're branching it into these two gains that we found for this practical implementation. So this is what we're going to run as our simulation. All right, so now I'm going to set from that previous step the KD and KP values. So it turns out that KD is just the K that we found from the root locus, and KP is the 0 times that gain. So the 4 times the 2 is what gives us the 8. And I'm going to run the system, the Simulink, just as I did before. So I'm going to pull out the reference, the output, the input, and the error, and we can track those over time as we go through this implementation. All right, so at the moment, I'm just looking at the output, and I'm just looking at the error. So using this PD controller, one, we want to make sure that, at least in simulation, it works. Yes, the error, I'm only doing this for 6 seconds in the simulation. The error goes to 0, which means that the steady state value of my output is going to eventually be equal to or asymptotically approach the reference signal. So I wanted 5 volts, and I see that I'm matching that. And if I see up here in my error, in my output, yes, I'm getting that 5 volts eventually. And it's behaving like a second order system, or it looks like a second order system. It's not entirely because I have that extra 0. But we see here I get some peak value. I'm eyeballing it for the moment as 5.2, about as the peak value. I do have some oscillations, but then it settles down into my steady state value of 5. Now, quickly, I do want to investigate the input effort a little bit. So let me just plot that quickly so we can see what it looks like. All right, so we see here with the limiter on, the most the input can be is set to 25. Again, I just picked that arbitrarily, but the controller is demanding more, but the system is only supplying 25. And then the input goes down, and then the input eventually goes to 0 into the system as it levels off. Right? But that limiter is why we have that hard cap there of 25. Without the limiter, there would have been an enormous spike up to near to a very high value, practically infinity there. Well, that's not really physically realistic to have. So here I capped at 25, but that's modifiable to whatever your real world system is capable of. All right, so going back to the output, because that's what I'm going to look at next, I want to validate how my controller responded in simulation. So first task, I drove the error to 0. The steady state value of my output was 5 volts. That's great. That's why I wanted it to be. That really has to be true before we can even go on and see the rest of the performance of our controller. Now let's look at what's the max value look like and the peak time. I can select other metrics here, that 5% settling time, rise time, depends what I'm looking at, what I'm interested in controlling in my final controller, in the performance of it. But I think that peak value and peak time, or max overshoot and peak time, are good things to look at here. So from the data, that's what I'm going to look at in 176, 177. I'm going to calculate the max overshoot from the simulation. So I'm just looking at my max value, or really the difference between the peak value and the steady state over the steady state value. That's what my max overshoot is defined as, because it's a percent difference. Right? And then I want to see when that happens. So I'm pulling the index using the max function, and then that same index on mytout is going to give me the time when my maximum is happening. All right, so it's saying that my max overshoot is 4.2% about. Do notice I'm doing 100 times that MP. So I get 4%, 4.2% as my max overshoot, and it's occurring at 1.63 seconds. I do want to just go into here just to verify at least by eye, am I picking the right point here? Scrolling over a little bit. Yeah, that does appear, at least visually, to match what I'm seeing here. That is my maximum value, about 5.2, which represents 4.2% above my steady state value. For a little bit better comparison, I'm going to go and kind of disable my limiter for the moment so I can get the true performance of a PD controller, assuming I could have this infinite input into my system. So I'm going to make the upper limit just really large here, 1 times 10 to the 8th, so I can get what the PD controller actually would be doing. And we'll see how, it's not really practical, but it's a good way to see the real performance without that cap. So if I rerun it now, it does change the output because I'm assuming that I can have just that enormous input going into my system. So now I see my overshoot actually is higher, about 6.7%, and the peak time is even lower, 1.18. So this is practically more what the true PD controller should be doing. And we can see what is happening to the input. All right, so we see the input is ridiculously high at the start, so it's just so high and then drops down relatively small. So in reality, we could not implement such a high input into our system. If it was a voltage, it would definitely burn it out if we were really requesting 10,000 volts immediately. But we can see what the performance of the system looks like if we had this perfect PD controller able to be implemented. So for the comparison here, I'll use that perfect infinite allowable input, and we see that the system performs with an overshoot of 6.7% and a peak time of 1.18 seconds. But let's compare that to the theory part that we skipped over a little bit here. Why did we choose the poles we did, the -2 plus or minus 2j? Well, in this example, it was just arbitrary, but in the future, we're picking them because of the desired output performance metrics. So let's see what would the expected performance metrics be with this chosen pole. All right, so we know that the poles are in the form of this -a plus or minus b times j, the real part and the imaginary part. As we've dealt with before, we can take the absolute value or the magnitude of a pole, and that's going to tell us the natural frequency. Well, that's just square root of a squared plus b squared. That's going to be the natural frequency of our system, of a baseline second order system. And then the damping ratio, there's different ways we can figure that out. Here I am going to use the simplest way to figure it out is the real part over the magnitude is going to tell us what the damping ratio is. So for this system that we were given with this arbitrarily chosen poles at -2 plus or minus 2j, it had the baseline system from the dominant poles should have a natural frequency of 2.83 and a damping ratio of 0.707. So it is underdamped. Well, we know that because the dominant poles are complex conjugates. And using this natural frequency and this damping ratio, the expected performance of the baseline second order system should have an overshoot of 4.32% and a peak time of 1.57%. Right? This is ignoring the fact that we added a 0 to our system. Now through simulation, where we do include that 0, that extra 0 at -4 that was added through the controller, we see that through the simulation, this is with the perfect input that was capable of just an infinite amount of input into our system, we did indeed see a higher overshoot, 6.7%, and a lower peak time, 1.18 seconds. And this was expected because that extra 0 in the left half plane should, from the baseline second order system, shift the max overshoot up and the peak time down. Now, when we put that limiter in, we're going to see a less drastic effect because we can't achieve such a high input, but we should still expect a higher than 4.32% overshoot and a smaller than 1.57 second peak time, and we did before. So we were able to control our system with this PD controller. However, from the root locus, it didn't perform exactly like we expected, because the root locus said, how's the baseline system going to perform? But through simulation, we were able to see how the actual system with that extra 0 performed. So we added a 0 to the system. We were able to select where that 0 was, and the dominant closed loop poles were set to a desired location of, in this example, -2 plus or minus 2j. So we selected the 0, and then we made the root locus, and we were able to find the appropriate gain from that for our system. Adding that extra 0, it was close to the real part of the dominant pole in our closed loop system. So we did see an impact on the performance in this case. Pulled up the overshoot, pulled back on the peak time compared to our baseline. Now, if we put the limiter in, the saturation in, it's going to perform a little bit closer because we can't have that infinite input into our system. But still, we should expect this change from the baseline system that we designed to. All right, so we, again, want to always do this simulation to validate how our system is actually going to behave, because it's certainly going to be different. It could be a little, it could be significant from what we're designing to. And we can get an idea by how close the third pole or an extra 0 is going to be from our qualitative knowledge, but the simulation is actually going to quantify it so that we can address it. And finally, we do want to keep an eye on that input effort, especially when we're using a derivative controller, because the peak amount could be extremely high and really not capable of it. And we want to keep an eye on the total input effort, because both of these are going to be impacted by the controller we choose. Anytime we have a derivative part in our controller, we're going to have this really big kick at the start of the system, because that slope, that rate change is so high as you go from an error of 0 to an error equal basically to the reference. But as the error and the reference start to get closer together, we're going to see that the derivative part input is going to go down. So one way we address this in this example is we could put a saturation or a limit on just the total input we could put into the system. But now the system is going to behave differently than how we predicted if we're using a derivative controller. But in the simulation, we can figure out how is it actually going to behave.